G'day everyone, welcome to Lubrication Explained. Today we're going to talk about PFPEs, which is kind of a fluorine polymer that is sometimes used as a specialty lubricant. It has very specialized applications and they tend to be outrageously expensive, which is why you don't commonly see them in industry. But if you've heard of PTFE, which is obviously Teflon, then PFPE is a very similar molecule, but it's obviously liquid at most operating temperatures and can function as a really oxidatively stable lubricant. So let's get into it. Alright, so let's talk about perfluoroalkylpolyethers. Now that is an absolute mouthful, so for simplicity's sake we generally just refer to them as PFPEs. Now, in order to demonstrate what a PFPE is, I'm going to take you from something that we recognize, which is, a hydrocarbon molecule, and substitute out various elements of it to get us to PFPE. So what I'm showing on screen here, straight chain hydrocarbon, and it's fully saturated, so there are no double bonds on it. We would typically call this an alkane. So no matter how many carbons it has, it's still referred to as an alkane. So an alkene would be something that has a double bond on it. Now, if this were a functional group, we would typically call this an alkyl functional group. If I substitute all the hydrogens out for fluorine, now what I have is a fluoroalkane. And of course, because everything is fluorine, I'm going to call this a perfluoroalkyl group. If I were to place an oxygen atom into the chain, what we know is that the single bond oxygen single bond is known as an ether functional group. So now I have a perfluoroalkyl ether. And of course, if there is more than one oxygen, then I would call this, a perfluoroalkyl polyether, because there's more than one ether. And that's how we build up to the name PFPE. Now, this in itself is not one of the molecules that you will see as a lubricant, but it gives you an idea for the backbone. There are generally 4 different kinds of PFPEs. I'm just going to show 2 of them today. PFPEK is a polymer that has a repeating group in the middle. So this group in the middle, which is inside the orange brackets, that will repeat n number of times, and that will give you a polymer that is PFPEK. Now, if I were to change the repeating group just a little bit and add a second repeating group, then I can get myself to a PFPEY. And I think there's also a Z and a D version as well, and they all have slightly different properties. We're not going to go into the details of the differences in this video. Now, just by looking at this, this structure, you can get an idea for some of the properties. So that oxygen molecule that was just bouncing around on the screen, it had nowhere to go, because when you look at the molecule, there are no double bonds, right, which are generally susceptible to the oxidation process. It can't substitute out for another oxygen because there's already oxygen there. What are you going to oxidize in oxygen? And it tends not to be able to attack fluorine because fluorine is more reactive than oxygen. So in many respects, there is nowhere for oxygen to attack in this particular molecule, and that makes them highly oxidatively stable. It also makes them really thermally stable as well. Fire resistant is another property of these, which I guess you could say is kind of linked to oxidative stability. But these come from a family of fluorinated compounds like PFOA or PFAs, where you might recognize these from fire retardant materials, whether that's fire retardant clothing or actual fire retardants. So this comes from the same family and shares those fire resistant properties as well. It's also very hydrolytically stable, so we don't have those same functional groups that we have on, say, an ester. So there's nowhere for a water to attack. And really one of the only ways that you can break these lubricants down is through the action of Lewis acids. So something like an aluminium chloride won't necessarily break down the molecule, but it will reduce the temperature at which thermal decomposition occurs. The other thing is that goes along with chemical stability is actually reactive stability. So these tend to be pretty non-reactive in the presence of radiation as well. So again, this is kind of related to oxidation stability because radiation is one of the things that tends to produce radicals. One of the other quirks about this molecule that you can see just by looking at it is it has virtually no polarity. So it's a little bit like a PAO in that respect, and it's very difficult to solvate additives in it. Now, because of that, our traditional additive chemistries don't work in PFPE lubricants. And in fact, you have to come up with a completely different additive chemistry. And the way that they get additives to solvate is that they have to make the additives look like one of these molecules. Remember, in a very simplistic term, like solvates like. So if you were to take this same backbone, eject the CF3 group on the end, and add some kind of functional group there that performs additive functions, that's what an additive would look like. So the backbone would help it solvate in the base oil, and then you would have some kind of reactive element that would do, EP work or anti-wear or whatever you wanted. The final thing to note as well is that they are very dense. So typically they're about 2 times as dense as a typical mineral base oil. And for our purposes, what that means is that you actually have quite a big difference between the absolute and the kinematic viscosity. So remember that kinematic viscosity is a viscosity that is taking into account the density of the lubricant itself. And most of the time we say that you can probably ignore the difference between absolute and kinematic viscosity because most mineral base oils, they're near enough the specific gravity of water. However, in this instance where it's a multiple of 2, that's going to have material impact on the kinematic viscosity. So where would you typically see these lubricants? Like what kind of applications demand such lubricants that are so different and so incompatible with other lubricants? Well, one area that you'll often see them is in the space and the aviation industry. So lubrication of O-rings, for example, in the space industry, that often happens by PFPE lubricants. Sometimes you'll see it in satellites and things like that. So they can sort of stand up to those really demanding temperatures. You'll also see them a little bit in the semiconductor industry, specifically on the vacuum pumps in the semiconductor industry. So often if you're working with highly reactive gases, like pure oxygen, for example, that's an instance where you might want a PFPE lubricant because it's so inert. It doesn't really react in the presence of a pure oxygen gas. You'll also see it a lot in nuclear plants, right? For obvious reasons, it's not susceptible to radiation, and therefore it makes it an ideal use case for PFPE lubricants. And one of the other places that you might see it is not actually in a robot that looks like this. I just pulled the generic image of a manufacturing robot, but really, really high precision manufacturing, because the traction properties of these lubricants are extremely good, and therefore you get very little stick slip, I guess you would call it, is familiar to anyone who's worked with metal working fluids. But they're so precise that you get very, very little error in terms of your machining tolerances. So that makes them ideal in that case as well. All right, this has only been a very introductory look at PFPE lubricants. There's a whole chemistry that goes behind it. But for the most part, most people aren't going to really see these in their career unless they're involved in very specialty applications. So I just wanted to give you kind of a rough idea of what they are and where they might be used. So as always, if you've got questions or comments, please leave them down below. Otherwise, this has been Lubrication Explained.